Speaker today will be Alina and Ostafe from the University of New South Wales, and she is going to speak to us on some GCD linear recurrences and unlikely intersection problems.
Thank you so much, Tom. And also thank you so much to all the organizers. It's an absolute pleasure to be here. It's my first time in Bristol, and also the first time I attend in person an ANS conference. I'm very happy. I'm not an algorithmic person, so I have to apologize in advance that there won't be algorithmic aspects in my talk, but I'll try to go over some problems and results, which I hope they will become of interest to you if they are new. And certainly these problems have not been considered from an algorithmic point of view. So I think it's a lot to explore in this direction. Okay, so as Tom already announced, I will mention some GCD, linear recurrences, and unlikely intersection problems. And these are really very much interrelated. So the motivation for this, for some of these results comes from the following basic question. Given integers a, b, what can one say about the GCD of a to the n minus 1 and b to the n minus 1? And in particular, prove that they are infinitely often coprime. And the first result in this direction was given by Bujocurva and Zanier in 2003, who proved that if a, b are multiplicatively independent, and I will formally define what this means, they don't satisfy a multiplicative relation, and let epsilon be bigger than 0, then for sufficiently large n, the logarithm of the GCD of a to the n minus 1 and b to the n minus 1 is at most epsilon n. So in other words, a to the n minus 1 and b to the n minus 1 do not share a large common factor. And although this is a very easy to state result, the proof lies on very deep Diophantine tools. And they also actually point in their paper that infinitely often there exists also a lower bound of the form n to the power c over log n. So in this talk, I'm sorry that it's cut from the slide. So in this talk, I'm interested in the function field analog of this question. So the basic question becomes, given polynomials fg over complex numbers, give upper bounds for the GCD, for the degree of the GCD of f to the n minus 1 and g to the n minus 1 for all n. So we want uniform bounds that do not depend on n. And of course, these are very special sequences of polynomials, in fact, linear recurrences of order 2. So one can ask more generally, given two sequences of polynomials, fn and gm, two interesting recurrent sequences, give uniform bounds for the degree of the GCD of fn and gm for all n and m. And some examples include, for example, take capital F and capital G to be multivariate polynomials and specialize them at powers of univariate polynomials, where everything, all the polynomials are over C. If F and G are linear forms, then again, these are two linear recurrent sequences. And one can also replace the powers with compositional iterate. Instead of the nth power, I iterate the polynomial n time. So for example, one can look at the GCD of f to the n minus some polynomial, g iterated n times minus the same polynomial. Or one can combine all these instances. For example, look at the GCD of x to the n minus 1 and f iterated n times minus 1. So what one looks at here is roots of unity, such that when you take the orbit at a root of unity under f, then this orbit contains at least another root of unity. So this is an instance of unlikely intersection problem, as all of these questions. So these GCD problems are intimately related to unlikely intersection problems. And in fact, some of them, they follow from finiteness results of such unlikely intersections. And these unlikely intersection problems are about intersection of parametric curves with torsion points. So here, torsion point means for me in the multiplicative sense, roots of unity. All coordinates are roots of unity. Division groups, or more generally, algebraic subgroups of the multiplicative group. So why are we interested in these problems? Well, I think they're just simply beautiful. So for me, I don't need further motivation, but having the opportunity to give this talk made me look for further applications of such results and problems to other algorithmic and cryptographic problems. For example, recently Sorenson and Webster, so these GCDs a la Bujoc, Corvaia, and Sanier in the number case appeared in recent work of Sorenson and Webster in finding strong pseudoprimes to several bases simultaneously. Also, such GCDs problems, so the result of Bujoc, Corvaia, and Sanier, or similar results, have been used by Luca and Sparlinski to give lower bounds on exponents of the group of points and embedding degree of elliptic curves over high degree extensions of finite fields, which are both related to cryptography. There are links to the theory of exponential Diophantine equations, such as Fm equal Gn for two linear recurrences, Fm and Gn, and to the Skolem problem, which I will discuss in more detail in the last part of my talk. The results of unlikely intersection of curves with torsion points, which is the Lang problem, has also been used to give lower bounds for the order of points on curves or higher dimensional varieties in reduction modulo primes as steps towards Kuhn conjecture regarding order of points on algebraic varieties. And the first results were given by Bolog in 2007 and 2010, but Chang improved these results using the global to local correspondence using Lang's problem and proving giving lower bounds in reduction modulo sufficiently large primes. And Chang, Kerr, Sparlinski, and Zanier, they obtained similar results for higher dimensional algebraic varieties. And such bounds can lead to explicit constructions of elements of finite fields of high order. Some of these results, for example, these results here, have also been used in the work of Bourgain, Gamburg, and Sarnag to describe the structure of solutions of the Markov equation in reduction modulo sufficiently large primes. Building on their work, Chen recently completed this characterization. And this has also been used recently to define a Markov equation-based cryptographic hash function by Fuchs, Lauter, Liebman, and Tran. So these are just some applications of unlikely intersection problems or GCD problems that I'll mention in this talk. So I will not discuss these applications. I'm not qualified enough to talk about them. But again, I will discuss the GCD and the unlikely intersection problems that come in such applications. So first, some notation and setup. So a central definition in this talk is the one of multiplicative independence. We say that as complex numbers are multiplicatively independent if for any non-zero integer vector, no such product of powers of alpha I is 1. Otherwise, they are called multiplicatively dependent. And similar definition holds for rational functions as well, so in the function field case. But I will also use multiplicative independence modulo constants or modulo a subset of the complex numbers, for example, a division group. And this means again that for any non-zero integer vector, no such product of powers of the rational functions is a constant in this case, or if it's modulo set S, is not in the set S. And GMN is the n-dimensional torus, so we take n-dimensional tuples of complex numbers where we do not allow zero components. And as I mentioned, torsion point means here in this talk that the coordinates are all roots of unity. All right. So I will start with some unlikely intersection problems. Then I will move to GCD problems, which will be consequences of finiteness results in this of unlikely intersection problems. And the last part of my talk will be about linear recurrences. So the underlying problem of these unlikely intersection problems is a result conjectured by Lang and proved by Haraser and Tate in the 60s. And it's about the presence of torsion points on plane curves. So let H be a bivariate polynomial irreducible, not of this special form, where rho is the root of unity. Then the curve contains only finitely many torsion points. So again, there are finitely many points with coordinates in roots of unity that satisfy this polynomial relation. Bjorkers, so we know that there are finitely many of them. Bjorkers and Smith, they gave a bound on the number of torsion points, which is about 11 degrees of H squared. And for Corvai and Zanier, they gave a bound for the maximal order of torsion points, which actually follows very easily from the proof itself, but the bound depends on the degree. The achievement of Corvai and Zanier is to give a bound that depends also on the genus of the curve. And when the genus is small, it wins over the bound that depends only on the degree. And since the orders are bounded, we can effectively find all such points. Let me now reformulate the result conjectured by Lang in the case of rational curves, because this will be the case that we will consider in this talk. So let Fg be multiplicatively independent, defining your curve. Then there are at most finitely many complex numbers such that both f of alpha and g of alpha are roots of unity. Yeah, so this is about the presence of torsion points on the curve f of t, g of t, as t runs over all complex numbers on the parametric curve. Now, this was about torsion points on plane curves. One can also ask about points on the curve for which the coordinates are not necessarily roots of unity, but of absolute value 1. So they are on the unit circle. So we can ask about finiteness of complex numbers such that f of alpha and g of alpha are of absolute value 1. And the first to consider this problem were Corvai, Masser, and Zanier in 2013. And they gave a finiteness result when f is just the identity, the f of x is x, and g is any polynomial. Well, g should not be a monomial, so again, x and g should be multiplicatively independent. And recently, Pakovic and Sparlinsky, they generalized this result to rational functions, and the result says that let fg be rational functions, then the set of alpha complex numbers such that f of alpha and g of alpha are of absolute value 1 is a finite set, and its cardinality is at most degree of f plus degree of g squared, unless there is a reason why this is not the case. And so here I say f and g is special. I'm not entering into details. They are this special here means it's defined in terms of Blaschke products. These are special Möbius transformation which take the unit circle into the unit circle. But we are in the context of polynomials, and this special here means precisely what I have already defined, that f and g are multiplicatively independent. Yes. And again, writing alpha as a plus ib. These two relations give you a system of two equations in A and B. Hence, once you know that there are finitely many of them, you can find all such points. Now, so Lang problem tells us about torsion points on curves, but we can also ask about higher order multiplicative relations of points on curves. So and this is the work initiated by Bombieri, Master, and Zanier in 1999, and they prove the following result. Let F1, Fs be rational functions over algebraic numbers, which are multiplicatively independent now modulo constants. Then the set of algebraic numbers such that these values, the specializations, are multiplicatively dependent is a set of bounded Weil height. If you are not familiar with the Weil height, I will not use it in this talk, hence I am not defining it, but it's a measure of algebraic numbers that takes into account all the absolute values in the number field that contains your number. So this is a set of bounded measure. It's infinite, it's not finite. Yes. For example, they call alpha such that f1 of alpha is a root of unity. You have infinitely many. The proof is effective and gives explicit bound for the height in terms of the initial data, F1, Fs, and the field over which they are defined. And let me also comment that this condition with constants is essential here, as otherwise the result is not true. As the following example shows, take F1 to be 2 times x, F2 x squared, then, well, these are multiplicatively independent, but not with constants. And there are infinitely many dependent values for which the height goes to infinity with m. So the result is not true if you just consider multiplicatively that the functions are multiplicatively independent. So this is when the values satisfy one relation. What about two independent relations? So when we have two relations, then of course we expect finiteness, and this is what happens. And this was actually proved in the same paper in 1999 by Bombieri, Master, and Zanier, but again under the condition that the functions are multiplicatively independent modulo constants. However, for these results, one does not need modulo constants. And this is what Morin proved. If F1, Fs are just multiplicatively independent, that's it, then there are at most finitely many alpha algebraic numbers such that the specializations of F1, Fs at alpha satisfy two independent relations. So for two linearly independent vectors, A1, As and B1, Bs. And an alternative proof was given in 2010 by Bombieri, Habegger, Master, and Zanier, who gave a different proof. So they give a different proof, which is also effective. So it gives a means to actually compute a bound of the number of such points. And this also leads to the following conclusion. If you have gamma, a finitely generated subgroup of algebraic numbers, and F1, Fs multiplicatively independent modulo gamma, then there are at most finitely many algebraic numbers such that the specialization fall in gamma. So they are not one here, they fall in gamma. And this is the statement that I will need for the GCD problem that I will talk later on. So there are finitely many alpha such that when you specialize, the points on the curve they are multiplicatively dependent modulo gamma. All right. Now I will mention, before finishing this first part, another type of unlikely intersection. And this is a result of Amoroso, Maser, and Zanier, which says the following. Let AI, Fi be rational functions such that these ratios are non-constant. Then there exists an effectively computable constant C, which depends only on the initial data, such that if for any n larger than this C and any alpha, this polynomial at alpha is 0, then the height is bounded. And here I present it in this, the result is much more general. I present it in this form because this is related to linear recurrences, as the form indicates. I will consider linear recurrences in the function field case, and I will specialize them when I will discuss about the Skolem problem. And this is why I present it in this way. So in other words, if AI and Fi are polynomials, then this tells us that for every given D, there are only finitely many monic polynomials h of degree D such that h divides a polynomial Fn. Yes?
Okay. You're not saying this holds for all alpha, it's saying for all alpha if that holds.
If this holds, then the height is bounded. Yes. If AI, assume that AI are constant here. This is also an unlikely intersection type problem because what we have here is points on the parametric curve defined by Fi such that the nth power of the point in the multiplicative setting belongs to a hyperplane if these are constant here. And the result is more general, is looking, for example, on at points on curves such that some power of the point belongs to an algebraic variety. So it's more general. Yes, it's more general. And here, this Fi can also be in a finitely generated group, so not necessarily nth powers. All right, so this is the result, and this is the comment that I made regarding unlikely intersections. And let me also mention that a similar result was obtained by this team of people. But now I want to ask the following question. Okay, so we know that if we take roots of one polynomial, then the height is bounded. But what if we look at alpha, algebraic numbers, such that satisfy two such relations? One should expect that we get finiteness. And this is not known. So it will be nice to prove such a finiteness result. All right. So this is the first part about unlikely intersection problems. And now I will use these problems to translate them into GCD problems. So let me start with the first result, that is that of Alina and Trutnik. So they consider polynomial Fg, which are multiplicatively independent. And they show that for all n, there exists a polynomial h such that all these GCDs divide h. And this h is defined only by the initial data f and g. And moreover, they also prove that if GCD of f minus 1 and g minus 1 is 1, then this f to the n minus 1 and g to the n minus 1 are coprime infinitely often. Something that in the number case is completely open. For example, one cannot, there is no proof that 2 to the n minus 1 and 3 to the n minus 1 are infinitely often coprime. And this is, of course, comes from torsion points on plane curves, right? Because here, when we look at the GCD, we look at common roots. That is, we look at specializations alpha such that f of alpha is a root of unity, g of alpha is a root of unity. And one should control also the multiplicity, which is very easy to construct the polynomial h. And let me remark that by Belkers and Smith, one has the following bound for the degree of h, which is, so this comes from the number of torsion points, and the power here comes from the multiplicity of the roots, of the common roots. This result has been generalized to S units by Corvai and Zanier. So if we have UV to be rational functions, which are multiplicatively independent, here S units means that all their zeros and poles are in the set S. Then they prove that the degree of the GCD of U-1 and V-1 is at most maximum of the degrees of U and V to the power 2/3. And the result is more general. They consider rational functions on algebraic curves, and the constant implied constant here depends also on the genus of the curve. So if we consider U to be F to the N and V to be G to the N, as in the previous case, then this bound translates into N to the 2/3, which is not uniform with respect to N. However, surprisingly, if you take conjugates of all these roots, one can recover the finiteness in Lang's problem and in the Eilon-Rudnick result that we saw on the previous slide. Now, this talk is not in the setting of finite fields, but I think it's still worth to say just a few words what happens over a finite field. So the exact analog of the Eilon-Rudnick result does not hold over finite fields. So let Fg be non-constant polynomials. And of course, if the powers here are multiple of the characteristic, then you always have a large common factor. However, even if you don't cheat with such exponents, Silverman showed that in fact, one still does not have same uniform bound as in zero characteristic. So for example, take f of x is x. This is an example given by Silverman. G of x, x plus 1, and take n to be congruent with -1 modulo p. Then the degree of the GCD of these two polynomials is n-1, since one can see that any element alpha which is not 0 and -1 is a root. So we do not have the same result. And Silverman generalized this example to every polynomial f and g and more general exponents. And he showed that for any non-constant polynomials f and g, there exists a constant that depends on the initial dot on f and g, such that the degree of the GCD grows with n for infinitely many n. So we do not have a uniform bound in this setting. And Corvai and Sanya, again, they consider the S unit case. So let S be a finite set and UV to be multiplicatively independent rational functions, modulo constants with non-zero differentials and with all the zeros and poles in S. And let D to be maximum of the degree of U and V. And they show that actually a similar result as in characteristic 0 holds for small degree compared to the characteristic. So the degree of the GCD of U-1 and V-1 is at most maximum of D to 2/3 and D squared over P. Which of course is non-trivial when D is at most P. So D again is the maximum of the degree of U and V. And if D to the 4 is at most P to the 3, so this wins and we have same bound as in characteristic 0. And let me finish the finite field comments by saying that these are actually related as well to older work. So if you take u to be x to the d and v to be 1 minus x to the d, then this is really a question about the number of solutions to x plus y equal 1 in variables from the subgroup of order B of this field. And this dates back to work of Garcia and Bollock and Hess-Brown and Koniagi. So it's related to much older work. And here I just mentioned that there is follow-up work after Silverman by Gioca, Hasia, and Tucker, and they considered generalization of the GCDs that Silverman considered to such GCDs where G1, G2 are polynomials over a field of positive characteristic. So this is the case of finite fields. And now I come back to characteristic 0. So again, Corbay and Zanier, they proved that the degree of the GCD of u minus 1 and v minus 1 is at most maximum of the degree of u. Yes?
So before you mentioned, I think you do a rational function. Is it best for polynomials?
Here you can, the GCD, you look at the degree of the GCD of the numerators. You can take them also rational functions, but you look at the GCD of the numerators of the polynomial. Yes.
3 is just the maximum.
Yeah. So this is the result of Corbay and Zanier. And now the question is, can we get, so there is their bound depends on the degree of u and v. So again, if you take u to be f to the n and v to be g to the n, it depends on the exponent. And the question is, can we get a uniform bound when u is such a product of polynomials and v is such a product of polynomials? So I don't want to depend on the exponents and I and I. And if one restricts the polynomials to being defined over number fields, one can achieve uniformness, and even in the more general case of GCDs of a polynomial H1, which is univariate, specialized at this product, which is this one, and H2 specialized at this product. So we have the following generalization of Alon and Trutnik. Let gamma be a finitely generated group, and all the functions fi, gi are polynomials, which are multiplicatively independent modulo of the group. Then there exists a polynomial h, depending only on the initial data, such that for any univariate polynomials of fixed degree with roots in gamma, the GCD of these two polynomials divides h. And of course, considering the factorization of H1 and H2 into linear factors, one reduces the problem to looking at such GCDs, where this omega 1 and omega 2, they belong to gamma, since the roots of these two polynomials are in gamma. So we reduce the problem to looking at such GCDs. And this is exactly the case of intersection of parametric curves with algebraic subgroups that I mentioned. That is the results of Bombieri, Masser, and Zanier, and the extension of, the generalization by Morin by considering the functions just being multiplicatively independent. So the proof follows. Oh, sorry, you don't see it because of this. I'm sorry. So here it's written Morin, yes, the result of Morin on finiteness of such points on curves implies that there are finitely many alpha, such that x minus alpha divides this GCD. So we have finitely many roots. And then we also have to control the multiplicity of such roots, of such polynomials, which one can do using the Mason's polynomial ABC. And this put together, of course, gives you a way to construct the polynomial H, for which this GCD divides H. And let me mention that when S equal 1 and R equal 1, that this is really a question about intersection of plane curves with division groups. And we know that the height of such alpha, so such roots, and the degree, so we have explicit bounds, which will give us an explicit bound for the degree of such polynomials, which in general is not available. So the result of Morin is effective, but no bounds have been worked out. Let me also mention that there is also a very deep work by Levin and Wong, and they also showed the following result. Let Fg be multivariate polynomials, which are coprime such that not both vanish at 0. Let G1, GL be multiplicatively independent with constants, polynomials which are univariate. Then they prove that the degree of the GCD of F specialized at these powers and G the same is at most epsilon K, provided that K is large enough. Here, large enough means in terms of epsilon. So this is the result that they prove. The result is not uniform, it depends on the power K. And it will be nice to give results that are uniform, so bounds that are uniform. So if F is H1 of this x1 times xr and G is this polynomial, then we have the uniformness, we have a uniform bound from the previous result. I should also mention that the result of Levin and Wong are more general. They apply actually to meromorphic functions. And here GCD means common zeros. And they are based on Alina theory. So it's a different game. The result is much more general. But if F and G are linear forms, then this is a linear recurrent sequence, and the same for G, which brings us to the last part of the talk, GCD of linear recurrences. So let F and Gn be two simple linear recurrences that are defined in this way. And here, simple means that these polynomials here, they do not depend on n. This is what simple means here. Let me recall the problem that I mentioned after the result of Amoroso, Master, and Zanier, that we would like to show under some conditions that the set of algebraic numbers, alpha, that are roots of any two polynomials Fn and Gm is a finite set. So this should be a very unlikely event. And this will already give, so this will give that there are finitely many alpha such that x minus alpha divides the GCD of these two polynomials of Fn, GCD of Fn and Gm for some n and n. But what we really want is to have some uniform bounds. So we want the degree of the GCD to be uniformly bounded for all nm, which will actually be a uniform function field analog of the results that are known in over number fields, in the number case, sorry. So yes, over number fields. Of course, we don't even have finiteness, so it's just a dream to even think for the moment of having uniform bounds. Let me mention that if k equal 2, this actually follows. So k here is the number of summons, and so if for both they are both linear recurrences of order 2, then actually this follows from Bombieri, Master, and Zanier because one can reduce to the multiplicative case. But if k is larger than 2, then no results are known. Now, this is also intimately related to the famous Kolem problem, which says that given a linear recurrence, un, decide if there is a 0, there is an n such that un is 0. So let me define S of un to be the set of n such that un is 0. And the famous Kohler-Mahler-Lech theorem says that the set S of un is the union of finitely many arithmetic progressions and a finite set. And if the sequence is non-degenerate, so what does this mean? It means that you have a linear recurrence, and to any linear recurrence, you have a characteristic polynomial. You factorize that polynomial into product of linear factors. And if the ratio of any two roots is not a root of unity, we say that the sequence is non-degenerate. In that case, the set of zeros is finite. Now, there are many results giving bounds for the number of arithmetic progressions or for the cardinality of the set of zeros when it is finite. And such bounds were given by Van der Putten and Schlickeve-Schmidt, Everts-Schlickeve and Schmidt in different cases. But the best result, I think, so far is one by Amoroso and Viada, who significantly improved the previously known bound. So you can write the bound of Amoroso and Viada on 2 lines. For the previous bounds, you need 3 lines. And all these bounds depend only on the order of the sequence. There are also non-uniform bounds, which depend on the characteristic roots, which may be of use for various applications that need information on the roots. And for example, such a result was given by Van der Putten and Schlickeve. But of course, all these bounds on the number of zeros or the number of arithmetic progressions does not tell you if the sequence has a zero. If in the non-degenerate case, because this is the interesting case. So we don't have a bound for the size of zeros when the set is finite. So the Skolem problem has been settled in the following cases, only for linear recurrences of orders 2, 3, and 4. For linear recurrences of order at least 5, the problem is open. And Shah more recently gave a result for simple linear recurrences of any order with the usual condition on dominance of the roots, so with 2 dominant roots. He gave an explicit lower bound for n such that un is not 0 from that stage. Let me also mention, before I come back to specializations, that so in the previous results, several conditions have been put on the linear recurrence, either on the order or on the dominance of the roots. However, a new point of view has been very recently introduced by Luca, Wankin, and Vorel. And they said, well, why don't we, so let us not put restrictions on the sequence, but let us reduce the domain where we look for zeros. And they define the so-called universal Skolem set, which is an infinite subset of positive integers, such that if I give you any linear recurrence, you can decide if that recurrence has a zero in that set. And this for any linear recurrence, hence the name universal. So this has been actually very recently introduced in 2 papers, 2 conference papers. And their first construction in their first paper is, for example, the set of Sn, where Sn is defined in this way. So they prove that this is a Skolem set, a universal Skolem set. However, this is a very sparse set of density 0. And they also gave in a second paper a more involved construction for which they can prove that it has a positive lower density, and also conditional on some assumption on the distribution of primes. They prove that they can prove, they advertise that they can prove that it's of density 1. So they announced it as a remark at the end of their second paper, but the details have not appeared yet. But now let me come back, please, to specializations. So we consider linear recurrences in the function field case. So these AI, Fi are polynomials. Well, here are rational functions. Now, if we look at zeros, alpha, specializations alpha, such that Fn of alpha is 0, then Amoroso, Maser, and Zanier tells us that the set of such algebraic numbers is a set of bounded height. And what we do is we also give a bound for the largest zero in all but a set of bounded height specialization of such polynomials, which shows that the Skolem problem is effectively decidable for specializations as above of such polynomials. And let me also mention that the Skolem problem is actually settled over function fields by Fuchs and Peto. So to state the result that we obtain, let me define an exceptional set. So here, when we specialize, we have to make sure that we don't get a degenerate sequence, because then we might have infinitely many zeros. And for us, it's also so we exclude alpha, such that such ratios are roots of unity. And it's also convenient to exclude roots of AI and Fi, which are finitely many. So the result is the following: let AI, Fi be rational functions, non-zero, of degree at most d, such that these ratios are non-constant. Now assume that for any such pair of ratios of our functions Fi is non-exceptional. Here non-exceptional means it's not defined by Blaschke products, because I will make connection to actually looking at unimodular points on curves. So we need a condition from Pakovic and Sparlinski. Then for all but at most d squared times k to the 3 elements alpha outside of the exceptional set, any zero n such that Fn of alpha is 0 satisfies. So it's bounded by x, a constant c d alpha to the power 4, where c is a constant that depends on the initial data, and d alpha is the degree of the smallest Galois field K, which contains alpha. So we have a bound for the 0 in such a linear recurrence, which depends on alpha. And the proof, let me, before I mention a few ideas behind the proof, let me mention that this also gives us the following conclusion. So if we are in the previous case, and we also need this condition, which actually comes from the generalization of the ABC theorem, then the splitting field of such polynomials is of degree at least a constant that depends on the polynomials AI, Fi, log n to the power 1/4. So we also obtain as a consequence such a result on the degrees of the splitting fields, which was actually announced already by Amoroso, Maser, and Zanier in their paper, but we give an explicit lower bound for such degrees. And this also says that apart from a finite set of polynomials, the degrees of the irreducible factors of such polynomials tends to infinity. So in the last minutes, let me mention just a few ideas behind the proof of this result. So let alpha be an algebraic number which is outside the exceptional set, such that alpha is a root of Fn. I already mentioned dominant roots in previous results, but let me define it now. So the characteristic Fi of alpha are called characteristic roots of the linear recurrence. And we say that it's a dominant, Fi of alpha is a dominant root if the absolute value is maximal among all the other. So now the proof goes quite easily. If one has a dominant root, then it's easy, because say that F1 of alpha is dominant, then this will grow much faster than the rest. So you get that n is bounded. If one has two dominant roots, then one can show that, so the result of Shah tells us that n is at most this bound, which depends on the height of alpha, and again, the degree of the smallest Galois extension over Q that contains your element alpha. Then Amoroso, Master, and Zanier tells us that height of alpha is bounded uniformly. So then we obtain a bound of this type. But we need to consider also 3 dominant roots, at least 3 dominant roots. And when we have at least 3 dominant roots, that is, we have relations of this type, we reduce the case to looking at unimodular points on plane curves. And this is exactly the result at the beginning that I mentioned of Pakovich and Shvalinsky, that the set of alpha such that F1 of alpha and F2 of alpha, here F1 is Fs over Fr and F2 is Ft over Fr. So the set is finite and the cardinality is bounded by this quantity unless something very special happens. And this will conclude the proof, putting all these results together. So we have results on the Skolem problem, we have results on unlikely intersections here that lead to the bound that I mentioned in the previous slides. So let me finish by mentioning 2 problems. So first one, sorry, the bound here on the 0 depends on alpha. But here alpha, I run over all algebraic numbers. What if we reduce the domain? Can we get a bound that is uniform? For example, we reduce the domain to roots of unity. So what if we restrict alpha to being in a special subset of Q bar, say roots of unity? That is, we look at alpha in Q bar such that alpha to the n is 1 for some n, alpha is a root of unity, and alpha is also a 0 of another linear recurrence. If we can prove finiteness in this case, then again, the degree of the GCD, since this has only simple roots, the degree of the GCD is uniformly bounded. And more generally, one can look actually at not roots of unity, but the cyclotomic closure of K. That is proof of a finiteness result for alpha in Kc, such that Fn of alpha is 0 for some n. And this will be, so one achieves this if one looks at the Bombieri-Master-Zanier result on multiplicatively dependent points on curves. If one reduces points in the cyclotomic closure, actually you need only one relation to obtain finiteness. So this is one problem. Another problem is, so here we consider in the previous, okay, let me, sorry. So here we consider nth powers of Fi as n, where n is at least 1. What if we consider S units? So we consider elements in a finitely generated group, not necessarily nth powers. Can we still get a bound on the degree of the elements in the group? So let me, so this is the formal question. Let gamma be a finitely generated subgroup and fix A1, AK. Then Amoroso, Master and Zanier, the result, as I mentioned, it's more general. They prove that for any U1, UK in the group that satisfies certain conditions, the set of alpha in Q bar such that alpha is a 0 of this polynomial is of bounded height. So we know that the set is still of bounded height in this more general setting. And let me also call that a solution alpha in this set is called primitive if ui of alpha is 1 for some I. Then the question is it true under some natural condition on your group that outside of a set of bounded height for every alpha in this set, the maximum of the degrees of ui is bounded only in terms of the degree of alpha and the coefficients? So this will be the generalization of the previous result for linear recurrent sequences. And I think it's time for me to stop. Thank you very much.
Yeah, do we have any questions?
Back to right in the beginning, we had the conjecture about the A over K minus 1, A minus 1. So the theorem was found by epsilon K, epsilon larger K. Is there any conjecture about what is the I want to say the correct order of growth. It all kind of makes sense because the function jumps around.
So,
some nice simple function that balances.
So as I said, there is also a lower bound, which is true for infinitely many n, which is of the form n to the power c over log log n, which actually comes from a result of Adelman, Pomerance, and Ramley. And what is believed is that this is also an upper bound for an appropriate constant c. Yes, so this is what one would expect, but nothing nothing has been proven. So it will be nice to have an upper bound of the form f of n, such that f of n over n goes to 0.
Yeah. And are there any bounds for the sort of primes that show up in the GCD? I guess you expect it to be lots of small primes, there are occasionally crazy large ones that you don't expect.
I don't know if such information has been, and if the proof actually gives you anything on this. So the proof is based on the Schmidt's subspace theorem. It's not effective, first of all. Yes, so so I don't think anything. I don't know if anything is. Okay.
So is there any hope if you say, ask the same question about the GCD of the 2 a to the n minus 1, a to the n minus 1, say you have 3, then you do better?
I think there are results. There are general. There are results. I don't know if for more GCDs, if you take more GCDs,
Just like common GCD of the 3 factors.
maybe one can do a bit better, but and there might be results like by Florian Luca, and so there might be results in this direction. People consider various extensions, various cases. Yes. But again, the results are not effective. Everything in the number case, as I'm aware, nothing is effective because of the Schmidt subspace theorem that is involved. Sorry.
Okay. Did you go to slide 24? Sorry.
No, that's okay. I mean, I'm sorry for everyone. Not,
Sorry.
no. Yes.
So yeah, you said that this construction was so you said this was effective. You can construct this polynomial. So I was wondering if what sort of complexity of this construction is.
So here is everything. You have to find the set of points on algebraic curves. I mean, on your curve that satisfy two multiplicative dependencies. That is Bombieri-Master-Zanier.
Okay.
If you find this set, then it comes for free. You just take the product of. You know that this is a finite set. You take the product of these linear factors and you raise it to the multiplicities, which is in terms of the degrees of the polynomials fi and gi. So this is everything very explicit. The difficulty here is to make explicit the result of Bombieri-Master-Zanier and to effectively find this set. And this problem has not been looked at in an algorithmic way. So again, effective here does not mean efficient. And I don't know anything more than just brute force, just looking at all the points and check them that they satisfy.
Do you know any results like predicting the size of the finite set?
So here the size, okay. So the size, this is the height, yes, the height of the elements here. This comes, yes, it comes from Bombieri-Master-Zanier, and you can work it out explicitly from their proof.
Okay.
Yes.
Thanks.
So say anything about the effective constant in your recurrence discrete?
Sorry.
How effective is the effective constant in your recurrence discrete?
So here you can work it explicitly. Absolutely, you can work everything explicitly. We did not get our hands dirty. But if one does that, then you can, because you see, I apologize. So this constant here comes from actually from Shah, and he got his hands very dirty, and he worked out the explicit constant there. So it's in his paper.
Well, just a reminder, we've got a half-hour break now, and we resume again at 11. Let's thank Alina again for her talk.